So this is the first homework of 6370, Design and Analysis of Reconfigurable Systems. To begin with, we have rigged up a circuit of a 1-bit full adder using 2 XOR gates, 2 AND gates, and 1 OR gate. So once we rig up the circuit, we compile the design. So as we can see, the design is successfully compiled and we would be able to see the flow summary where it would tell us how many ALMs we have used, which is 2, and the total number of IO pins with all other information such as the DSP blocks. And once we see the flow, we will be able to see the timing analyzer and check the critical path for the system. So for this particular circuit, the critical path would be, so as we can see, the critical path for this particular circuit is going to be from C in to C out, and the delay is going to be 8.611 nanoseconds. Once we check the delay, now we can check the working of the particular circuit by extracting the HDL file and giving test cases and checking the output through waveforms. So this is the VHDL file which was generated from the schematic. And once we generate the VHDL file, we remove the BDF file and we set the VDH file as the top module. And to get the test bench, we generate from the template which I've already generated, and I'll be adding that particular test bench. So this is the test bench with the test cases modified, and we would run the simulation once again to check the compiled results. So as we can see, the design has again compiled successfully, and now let us open the RTL simulation. So we can see we have zero errors and warnings when we are loading the program. So let us simulate the program. Seeing the output waveforms of the 1-bit adder. So we can see that the design is working perfectly fine when we are seeing the input is 0, 0, 1, and we have the sum is equals to 1 and this carry is equals to 0. This says the design is working perfectly fine. Coming to the part 2 of the homework, where we are going to write the HDL code or the Verilog code for a 4-bit, 8-bit, and a 16-bit adder. So let us add our design. Now let us compile the design. So we have zero errors while loading the program. And now let's start the simulation. So we can see the operation of a 4-bit adder is working perfectly fine with all the test cases. So let us now simulate the structural model of the same design and check the input output pins and the ALMs used in the particular design. We have designed a 4-bit adder using a structural model, and now we are setting the top module as our particular design and running the simulation. So now we can see the design has been compiled successfully, and the total number of ALMs used is going to be 4, and the total number of pins we are using in this particular design is going to be 14. Now let us check the timing analyzer to check the critical path for the particular design. So the critical path for this particular design is going to be from node A1 to sum 3 with a delay of 5.9.519. Now let us check the simulated result through the RTL simulation to check the design to verify the particular design. So once low after starting the simulation, now we can see the results has been matched perfectly as expected from the truth table or from the design. So this concludes the 4-bit adder in schematic and behavioral. Now let us design the same behavioral and structural for the 8 and 16-bit adders. We have designed an 8-bit adder using the behavioral type with the design and the test cases. So now let us compile the design to check the working of the design. So once the design is compiled successfully, we can see the number of ALMs used is going to be 5 and the total number of input output pins used are going to be 26. Let us now see the critical path of the design. So the critical path for this particular design is going to be from A0 to sum 2 with a delay of 19.659 nanoseconds. Now let us check the simulated Now let us check the design using the RTL schematic view. So by checking the output waveforms, we can clarify that the design is working as expected by seeing the simulated results. Now let us design the 8-bit adder in the structural model. So now we have designed the 8-bit adder using the structural model. So this being the design code and this being the test bench. So now let us compile the design. So now we can see the design has been compiled successfully and the total number of input output pins used is going to be 26 and the total ALMs used is going to be 9. And now let us check the timing analyzer to check the critical path of the design. So the critical path for this design is going to be from node A1 to node Cout and the delay is going to be 15.566 nanoseconds. Now, let us simulate the RTL simulation. So after compiling and starting the simulation, now we can see the simulated results matches our expected output. So by this, we are concluding the structural model of the 8-bit adder. So now let us perform the same operations using the structure and the behavior model for the 16-bit adder. Now designed a 16-bit adder using the behavior model. So this is the design and this being the test bench with the test cases. So now let us compile the design to check the total number of input output pins used with the DSP modules. So once the compilation is successful, we can see the total number of pins used, which is 50, and the total number of ALMs used is going to be 9. So now let us check the critical path for the design. So the critical path for this design is going to be from node A0 to sum6 with a 16.174 nanoseconds of delay. So now let us compile the RTL simulation. So now once we compile the design, we can see the expected output results are matching the expected outputs. So with this, we are concluding the behavioral model of a 16-bit adder. Now let us do the structural one. So now we have designed a 16-bit adder using the structural model. So this being the design code and this being the test bench. So now let us compile the design to verify the working. So the design is compiled successfully and we can see the total number of pins used are going to be 50 with the total number of ALMs used are 19. So now let us check the critical path of the system. So the critical path for this particular design is going to be from Cin to node sum15 and the delay is going to be 20.886 nanoseconds. Now let us compute the simulated results with the waveforms. So now once we compile the design, we are able to see that the design is working as expected. So with this, we are concluding the first homework of the reconfigurable systems. Thank you.